Prove that 21n plus 4 all over 14n plus 3 is irreducible for every natural number n. IMO 1959 प्रॉब्लम। तो इस प्रॉब्लम में हमें प्रूव करना है कि जो फ्रैक्शन है ये इरिड्यूसिबल है। सो व्हाट इज द रिड्यूसिबल एंड इरिड्यूसिबल फंक्शन फ्रैक्शन? So for example, if we have a fraction like 5 over 3, so 5, we know that 5 over 3 is irreducible fraction. Since 5 and 3 do not share a common factor other than 1, since 5 and 3 do not share a common factor other than 1. So 5 and 3 share a common factor 1. That's why 5 over 3 is a irreducible fraction. But if we have a fraction like 4 over 2, so 4 over 2 will be a reducible fraction. Since 4 and 2 share a common factor, that is 2, so 4 over 2 can be reduced into 2 1 2, 2 2 4 into 2. So basically a reducible fraction are those fraction which can be converted into their simplest form, and irreducible fraction are those fraction which cannot be converted into their simplest form. So in this problem we have to show that 21n plus 4 and 14n plus 3 do not share a common factor other than 1. But in this problem we will apply a proof by contradiction. So suppose n plus 4 and 14n plus 3 share a common factor p. Let p is greater than 1. So if a fraction is a reducible fraction, then it must be share a common factor, and the common factor must be greater than 1. Here we can see 4 over 2 is a reducible fraction. Since 4 and 2 share a common factor, that is 2, and 2 is greater than 1. So we have to prove that 21n plus 4 and 14n plus 3 share a common factor p, which is greater than 1. So from here we can write 21n plus 4 and 14n plus 3 must be divisible by p. Since we have shown in the example that 4 over 2 is a reducible fraction, since 4 and 2 share a common factor, that is 2, so 4 must be divisible by 2 and 2 must be divisible by 2. That's why if 21n plus 4 and 14n plus 3 share a common factor p, which is greater than 1, so from here we can say that 21n plus 4 and 14n plus 3 must be divisible by p. By same logic we have concluded here. So from here we can also say that 20n plus 4 must be congruent to 0 mod p. Let's say equation first, and 14n plus 3 must be congruent to 0 mod p. Let's say see it's equation 2. So these are the two modular equation, and we have to solve them. So multiplying equation 1 by 2 and equation 2 by 3, we get, so we have to multiply equation 1 by 2 and equation 2 by 3 so that we could make the equal coefficient of n. So by multiplying equation 1 by 2 and equation 2 by 3, we get 42n plus 8 is congruent to 0 mod p. Let's see equation 3, and by multiplying equation 2 by 3, we get 42n plus 3 is congruent to 0 mod p. Let's say equation 4. So these are the two, and we are gonna treat these two like a system of equation. So subtracting equation 3 from 4, subtracting equation 4, equation 3 from 4. So subtracting equation 3 from 4, we get so by subtracting 3 from 4, equation 3 from equation 4, we get 1 is equal to 0. Remember, in the modular equation, we can treat the equivalent sign or 3 parallel lines with equal sign. So if we subtract 40n plus 9 is equal to 0, and 42n plus 8 is equal to 0, so we get 1 is equal to 0, and we will replace the equivalent sign. So from here we get 1 is congruent to 0 mod p. But this equivalence relation is only holds true in modulo 1. So if we have p is equal to 1, then in case of p is equal to 1, this equivalence relation holds true, and this is the only possibility. So from here we get p is equal to 1. So our p must be equal to 1 so that this modular equation could be true. And which is a clear contradiction. since we have assumed in the beginning that 21n plus 4 and 14n plus 3 share a common factor, p is greater than 1, p is greater than 1, and here we have got in the end that p is equal to 1. That is a clear contradiction, and we are done.